warahmatullahi wabarakatuh. Firstly, I will explain about the background of our study. Our study is about the pollutant in the Great Lakes. The Great Lakes are a series of interconnected freshwater lakes primarily in the upper Mid-East region of North America on the Canada-United States border, which connect the Atlantic Ocean through the St. Lawrence River. The Great Lakes consist of Lakes Superior, Michigan, Huron, Erie, and Ontario. The Great Lakes are the largest group of freshwater lakes on Earth by total area and the second largest by total volume, containing 21% of world's surface freshwater by volume. Although the Great Lakes are large, they are sensitive to pollutants from the Great Lakes are relatively small. They are less than 1% per year in comparison to the total volume of water. Pollutants that enter the lakes are retained in the system and become more concentrated with time. These pollutants include toxic, invasive species, and habitat degradation. First is to find out the mass of pollution of the Great Lake. Second, to solve the equation manually and by using computer algebra system, MAPL. And the third one is to determine the amount of pollution that will be decreased after some time.
Bismillahirrahmanirrahim. So now I will briefly explain about the model. The model that we choose is dm over dt equals to negative k mt. So what does each variable in the model represents? So first, mt is the mass of the pollutant with respect to time, and k is equal to r over v, whereby r is the rate water flow into and out of the lake, and v is the volume of the water in the lake. From the model, we assume that all sources of pollution have stopped. The pollutant does not biodegrade or decay through any other process, either biological, chemical, or physical process. Other water gains and losses in the lake, such as rainfall or evaporation, is considered isolated. The volume of the water in the lake is constant. Pollutant is always evenly scattered within the lake. Water flow into and out of the lake are at the constant rate.
As I had mentioned before, K equals to R over V. So as an example, for Lake Superior, V equals to 12.10 and R equals to 2.01. So we get K equals to 0.166. So this value we substitute into our model, so we get the x over dt equals to negative 0.166 xt. We obtained the parameters from Rainey 1967. We obtained the initial conditions for the system equations from Al-Sulami, Falcon, and Filipenko 2016. The initial conditions are as follows. We use this initial condition in our calculation.
So this is the manual solution for our project. This is the system of linear equation. The first equation is dx over dt equals to negative 0.166 xt. Second equation is dp over dt equals to negative 0.319 pt. Third equation is dh over dt equals to negative 1.441 ht plus 0.166 xt plus 0.319 pt. The fourth equation is dy over dt equals to negative 12.292 yt plus 1.441 ht. And the last equation is dn over dt equals to negative 4.134 nt plus 12.292 yt. The steps to solve the system of linear equation are as follows. First, perform Laplace transform on both sides of the equation. Second, solve the equation simultaneously. Third, perform partial fraction decomposition. And last one, do inverse Laplace. For equation 1, first, perform Laplace on both sides. Make xs as a subject, perform inverse Laplace. Then we get xt. For equation 2, first perform Laplace on both sides, then make ps as a subject, inverse Laplace on both sides, then we get pt. For equation 3, first perform Laplace on the both sides of the equation, make hs as a subject, and substitute xs and ps. Then do the partial fraction. Later perform inverse Laplace. Then we get hd. For equation 4, first perform Laplace on the both sides. Make ys as the subject. Substitute hs. Do the partial fraction. Later perform inverse Laplace. Then we get yt. For equation 5, first perform Laplace on the both sides of the equation. Then make ns as the subject. Substitute ys. Do the partial fraction. Perform inverse Laplace. Then we get nt. At t equals to 5, which means time equals to 5 years, we substitute into each equation. It's 5, we get 5.276 slugs, P5 0.998 slug, H5 0.971 slugs, Y5 0.116 slugs, N5 0.363 slugs.
This is the computer-aided solution for our project. This is the graph mass of pollutant versus time. As the time increase, the mass of pollutant decrease.
To conclude, we have studied the first-order differential equation to measure the mass of pollutants in each lake after some time. And results show that the differential equation can be solved using Laplace transform method. In this study, the observation is specified to 5 years and the mass of pollutants after 5 years is measured. The 5 years, Lake Superior has mass of 5.276 slugs, Lake Michigan 0.998 slugs, Lake Huron 0.971 slugs, Lake Erie 0.116 slugs, and Lake Ontario 0.363 slugs. In order to improve the accuracy of the model, it is recommended to consider other external factors that may have contributed to the pollution of the lakes. One of the top causes of lake pollution is agriculture, which include soil erosions, manures and synthetic fertilizer management, as well as the use of pesticides. This can produce effect towards the quality of the lake, which is nearby the agricultural area. Besides that, it is also recommended to acknowledge hydrologic modifications, which include presence of dams and other flow regulation structures and dredging activities that can give impact towards lakes' physical and chemical characteristics. Last but not least is pollutants from urban runoffs and storm sewers. By taking all of these outlying factors into account, we are confident that this model could be improved, hence enhancing the accuracy of the model.